We may already be closer to a second Earth than we ever imagined, and the first clues are hidden in tiny shadows passing across nearby stars. Tonight on The Galaxy Scientist, we drift into the quiet search for Earth-like worlds, planets with the right warmth, the right skies, and the soft promise of oceans still unseen. Astronomers are finding hints everywhere now, tucked inside faint dips of starlight and careful streams of data. If this brings you ease, a soft like and gentle subscribe help others drift here too. Now take a calm breath and drift with me toward those distant, familiar shores. Out in the quiet dark, far beyond the reach of any city light, there are worlds that never meet the human eye. They do not shine on their own, and they do not announce themselves. For most of our history, they were only guesses and daydreams, shapes imagined between the stars. Astronomers spoke of them like rumors carried on starlight, soft and uncertain. A slight dimming here, a subtle wobble there. Tiny changes that could so easily have been noise or error. For a long time, distant planets were more like ghosts than places, suggested by shadows and by the faintest tremble in a star's glow. Little by little, that changed. As our telescopes sharpened and our instruments grew more patient, those whispers began to gather weight. We learned to listen more carefully to the light itself, to treat every flicker and flutter as a possible message. New methods and sensitive detectors turned faint starlight into something we could measure with care. Suddenly, those faraway worlds were not just theories, but quiet companions, orbiting their stars in the deep, slow rhythm of gravity. Now, we are no longer simply counting exoplanets like distant dots on a map. We are beginning to read their skies in the pale glow that wraps around these alien worlds. Astronomers search for stories that have never been told aloud. A planet's atmosphere is delicate, almost invisible, yet it holds nearly everything that matters for understanding what that world truly is. When you hear the word atmosphere, you might think of air, clouds, maybe a blue sky or a storm. But around a planet far from home, that thin envelope of gas becomes something more. It is a diary written in molecules, a quiet record of what the planet has been through and what it might yet become. Each kind of gas is like a sentence in that diary, and the overall mix is the tone of voice. Within that thin veil, there are clues to how the planet was born, how it has changed, and what is happening on and under its surface. The atmosphere remembers ancient eruptions and slow chemical reactions. It remembers the warmth of its star and the cold of deep space. From that fragile layer alone, we can begin to guess at weather patterns, the presence of clouds or oceans, even the faint possibility that something living might be breathing beneath those alien skies, or that nothing living has ever walked there at all. Reading this kind of diary is not simple. We cannot open a cover and flip through neat pages. Everything is encoded, folded into the way light moves through gas. When we read an atmosphere correctly, it can tell us whether a world is a blistering giant shrouded in swirling storms, or a calmer, gentler place where water may pool and flow. It can hint at whether the winds scream across the planet or drift slowly like evening breezes. Sometimes, the clues are subtle, a trace of one gas here, a faint absence of another there, and from those tiny hints, an entire portrait begins to emerge. Certain gases speak with distinct voices. Carbon dioxide is one of them. On a distant world, a strong signature of carbon dioxide might point toward ancient volcanoes, slowly pouring gases into the sky over uncounted ages. Water vapor has its own soft language, When astronomers find water vapor in the air of an exoplanet, they imagine not only clouds but perhaps rain, mist, and, if conditions allow, oceans spread like ink over the surface. Methane is another storyteller. On some worlds, it can be formed by simple chemistry or by deep geological processes. On others, at least in theory, it could also be breathed out by life. None of these gases alone are proof of anything as dramatic as biology, but together they form a pattern, a chemical script that reveals what the planet has been doing in the dark. To the trained eye and the patient mind, an atmosphere becomes a text written in this quiet script. Instead of ink and paper, it uses wavelengths of light. Instead of letters, it uses atoms and molecules. The challenge, of course, is distance. How do we read something so delicate when the planet itself is so far away that even its star looks like a pinprick? We cannot fly there, not yet. We cannot hold a jar of that air in our hands. So we turn to the one messenger that crosses the emptiness with ease: light. Even though we will never touch most of these worlds, their light visits us, carrying stories across the dark. Every ray that reaches our telescopes has been shaped by the journey it has taken. Some passed through hot, turbulent regions near a star. Some slipped through the thin shell of a planet's atmosphere. Along the way, specific colors of light were absorbed or scattered by different gases. Hidden in that pattern of missing and surviving colors is the fingerprint of the atmosphere itself. To reveal that fingerprint, astronomers use a technique with a musical sort of name: spectroscopy. It sounds complex, but at its heart, it is built on a simple idea. When white light passes through a prism, it spreads out into a rainbow. In that rainbow, each color corresponds to a different wavelength, a different note in the song of light. If certain gases are present, they quietly remove, or sometimes add, specific notes. The rainbow will show tiny dark lines where light has been absorbed, and sometimes bright lines where extra light has been emitted. These lines act like the grooves in a record, holding information that can be played back by those who know how to read them. Scientists take the light from a star and its planet and stretch it into this rainbow, then study it in careful detail. They are not looking at the rainbow as a whole, but at the fine print etched within it. A dip at one set of wavelengths might point to water vapor. Another might hint at sodium, carbon monoxide, or methane. Each detection adds one more word to a language we are still only beginning to understand, a language spoken by planets. Among the many ways to use spectroscopy, one method has proven especially gentle and powerful: transit spectroscopy. Picture a distant star glowing steadily in the dark. Now imagine a planet passing in front of it, as seen from our vantage point, like a tiny moving silhouette. This crossing is called a transit. During those brief moments when the planet slips across the face of its star, a very small bit of the starlight has to pass through the planet's atmosphere before it reaches us. That thin ring of air acts like a filter. Astronomers compare the star's spectrum just before the transit, during the transit, and just after it has finished. The light from the star alone serves as the baseline. The light that has passed through the planet's atmosphere carries the imprint of the gases wrapped around that world. By subtracting and comparing, they can tease out extra absorption at particular wavelengths. Those small differences are like smudges left by invisible fingers, marks that reveal what kind of air the planet is breathing. The first time this technique truly proved itself was at the start of the new millennium. In the year 2001, the Hubble Space Telescope, quietly circling Earth above the glare of our atmosphere, watched as a giant exoplanet crossed its star. That world has a somewhat technical name: often spoken as HD 209458b. It is a hot, swollen planet, a so-called hot Jupiter, orbiting extremely close to its sun-like star. As this giant world eclipsed its star, a portion of the starlight filtered through the planet's outer layers of gas. When astronomers examined the spectrum, they saw a distinctive pattern. Certain wavelengths were more heavily absorbed, forming a signature that matched sodium gas. For the first time, humanity had clear chemical proof that an exoplanet possessed an atmosphere we could detect from light years away. For scientists who had spent their lives wondering about worlds beyond the solar system, that moment felt like a door opening. One of the leading voices in exoplanet studies, Alan Boss, spoke of this as the beginning of a new era. Detecting the atmosphere of an extrasolar planet was not just another item on a list of discoveries. It was a shift in what was possible. Until then, we could find planets, weigh them, and trace their orbits. Now we could begin to describe their skies. Transit spectroscopy became a key that fit this new lock. With Hubble and with other telescopes on the ground and in space, astronomers began to search alien skies on a routine basis. One by one, they pointed their instruments at stars known to host planets that passed in front of them. They watched those tiny dips in starlight and peeled apart the spectra, looking for familiar chemical fingerprints. Sodium showed up again on that first hot Jupiter and on others. Soon, water vapor was identified in the atmospheres of several giant exoplanets, followed by signs of methane, carbon monoxide, and other gases. We began to see that some giant planets are wrapped in thick, cloudy atmospheres, heavy with water and haze, while others appear surprisingly clear and dry. These differences told us that even two worlds of similar size and mass can live under very different skies, shaped by slight changes in temperature, chemistry, and distance from their star. Then came a gentle but powerful finding. Using Hubble once again, astronomers turned their attention to a smaller, milder exoplanet with a name that sounds almost like a code: K2-18b. This world orbits within the region around its star, where temperatures might allow liquid water to exist, a place often called the habitable zone. When its transit light was studied through the lens of spectroscopy, the telltale signs of water vapor appeared in its atmosphere. It was the first time water had been clearly seen in the air of a small, temperate exoplanet, lying within its star's potentially habitable band. K2-18b is what astronomers call a super-Earth, a planet with a mass about 8 times that of our own home world. That makes it heavier and likely larger than Earth, but not as enormous as the great gas giants. Its moist skies stirred excitement across the globe. The reality, as scientists gently remind us, is more complex. Some argue that K2-18b may be closer to a mini Neptune, a world with a thick envelope of hydrogen and gas surrounding a possible icy or rocky core, rather than a true Earth-like twin. Even so, the detection of water vapor there carries a quiet weight. It shows, beyond theory and hope, that we can actually find worlds with key ingredients linked to habitability, even when they orbit stars many light years away. On K2-18b, whatever its exact nature may be, the presence of water has become a decisive factor in how we see it, turning a distant point of light into a place worth wondering about again and again. Water in the skies of K2-18b was a quiet turning point, but it was only one part of a much larger tapestry. To glimpse that tapestry more clearly, astronomers have had to learn not just one way of listening to distant worlds, but several. The first, using transits. reads the way a planet dims its star and filters starlight through its air. Yet, gentle as that method is, it is not the only path we have. Sometimes, instead of watching how a planet changes its star's light, we try to see the planet itself. This is called direct imaging, and it is a little like cupping your hands to block a street lamp so you can spot a tiny firefly nearby. Stars are blindingly bright compared with their planets, outshining them by millions or even billions of times. Against that glare, a planet's own glow is almost impossible to see. Almost, but not entirely. Astronomers use special devices called coronagraphs, masks placed inside a telescope that block out most of the star's harsh light while leaving the surrounding space visible. In some designs, there are even separate instruments set a little distance away in space, like a shield, whose only job is to hide the star so the telescope behind it can watch the fainter companions. When this works, the star becomes a muted blur, and around it, the delicate points of light that are planets can finally step out of hiding. In the year 2008, one of the most quietly breathtaking images in astronomy appeared. Against the darkness, there was a star known by its catalog name, HR 8799. Close to it, not just one but 4 tiny dots of light were seen, each moving slowly around the star over time. It was, in a sense, the first family portrait of another planetary system. These 4 worlds are giants, each several times more massive than Jupiter, glowing in the infrared like warm embers around a fire. For years, astronomers watched these 4 planets trace their orbits, measuring how fast they moved, how far they sat from their star, and how their paths were arranged. It was as if we had been staring at a distant house and suddenly realized we could see the pattern of its rooms and hallways, the layout of a solar system that was not our own. At first, these direct images mainly showed positions and motions, where the planets were, and how they danced around their sun. But as our tools grew more sensitive, we learned not just to see those distant worlds, but to taste their light. In the spring of the year 2025, the James Webb Space Telescope turned its golden mirrors toward HR 8799 and captured the clearest infrared images of this system yet. Instead of looking only at how bright the planets were, astronomers gently spread their infrared glow into spectra, thin bands of color beyond human vision. Within those bands were the signatures of the gases in their atmospheres. What they found was rich and telling. The 4 giant planets of HR 8799 showed strong signs of heavy elements, particularly in the form of carbon and oxygen. The spectra carried prominent fingerprints of carbon dioxide, a gas that forms under specific conditions and hints at a certain way of building planets. These patterns suggested that these giants likely grew as solid cores first, small rocky or icy seeds that slowly gathered gas from the surrounding disk, much like we believe Jupiter did in our own system. Astronomer William Balmer, whose team worked on these observations, described the feeling as more than simply seeing distant points of light. With direct imaging spectroscopy, he explained, it is as though we are sampling their air, learning the ingredients of their skies and, in a quiet way, how those worlds were assembled piece by piece. It is a reminder that even from light years away, we can trace the history of a planet woven into the chemistry of its atmosphere. There is yet another way to study far-away worlds, one that does not rely on blocking the star or catching a transit alone. Instead, it builds a kind of thermal portrait, a map made from temperature. When a planet circles its star, there comes a moment when it slips behind the star from our point of view. This is called a secondary eclipse. During this brief hiding, the planet's own light, especially its infrared glow, drops out of the total signal we receive. By carefully measuring the overall infrared brightness of the system before and during this eclipse, astronomers can tell how much light was coming from the planet itself. If they repeat this at different wavelengths, they begin to see how the planet's dayside temperature changes from place to place and color to color. This technique, known as eclipse mapping or phase curve mapping, lets them sketch a very simple weather map of a world they will never visit. With precise timing and instruments like those aboard the James Webb Space Telescope, scientists can notice if one side of the planet is much hotter than another. A large temperature difference might hint at sluggish winds and cloudless skies, where heat piles up under the constant glare of the star. A smaller difference could suggest thick clouds, fast winds, or other processes that spread warmth more evenly around the globe. Tiny changes in light become hints of storm patterns, jet streams, and shifting cloud decks on alien worlds. One of the early famous attempts at this kind of mapping involved another hot giant called HD 189733b. Using the Spitzer Space Telescope, astronomers traced the infrared light from this planet as it moved through its orbit. They discovered a giant hotspot on its dayside. A region warmer than the rest shifted away from the point directly beneath the star. That shift told a story of fierce winds whipping around the planet, carrying heat downwind and reshaping the climate pattern. We were, in effect, watching the weather on a world that exists only as a tiny point in our images. Since then, eclipse mapping has grown more refined. While we are still far from resolving detailed continents and coastlines, the dream is that one day, for certain Earth-like targets, subtle differences in brightness and temperature could hint at contrasts between land and ocean, or between clear skies and cloud-covered zones. For now, even the coarse maps we can build feel astonishing. Temperature stripes, drawn across a world many light years away, derived from almost imperceptible dips in light. Taken together, these methods, transits, direct imaging, eclipse and phase curve mapping, along with other tools still being sharpened, form a gentle but powerful toolkit for exploring distant atmospheres. To the eye, the raw data does not look like a planet. It looks like lines on a graph, jagged curves, small shifts in brightness across time. Yet, for the scientists who study them, those lines are not abstract at all. They are revelations, whispered in numbers, each bend and dip transforming a cold point of light into a place with character. From a spectrum, we can imagine clouds or hazes thickening the air. We can picture calm skies or choking, poisonous mists. Strong signatures of water might suggest tranquil seas below, or at least the possibility of rain. Signs of certain gases could hint at erupting volcanoes, storms of dust, or oceans of strange chemistry. The atmospheres become mirrors of the worlds beneath them, and as we read them, our mental map of the galaxy fills not just with positions, but with personalities. What makes this so moving is that we are still at the beginning. The revolution in what is possible has only just begun to unfold. Even so, we already have a kind of scrapbook, a collection of firsts and milestones gathered over the past 2 decades, each one adding a new note to the quiet song of exoplanet science. In the year 2001, that same hot Jupiter, HD 209458b, gave us the first clear atmospheric fingerprint of an exoplanet, sodium in its skies. It was a simple detection, just one element's signature carved into the spectrum, but it marked the start of remote sensing of alien atmospheres. For the first time, we were not just guessing what might be there. We had direct evidence. By the year 2007, both the Hubble Space Telescope and the Spitzer Space Telescope had joined in this work, turning their eyes toward another scorched world, HD 189733b. In its blistering atmosphere, they found water vapor. This did not mean oceans or gentle rain, not on such a hot, violent planet, but it proved that even gas giants heated nearly to a white-hot glow could harbor water in their air. Astronomers began to talk about clouds and hazes on planets far more extreme than anything in our own system. A few years later, in the year 2013, a ground-based telescope equipped with a remarkably precise spectrograph added a new kind of detail. Observing HD 209458b once more, researchers detected carbon monoxide winds rushing through its atmosphere at thousands of miles per hour. For the first time, we were not only measuring what the atmosphere was made of, but also how it moved. It was a direct glimpse of weather on an exoplanet, not just temperature, but motion, wind, and flow. The discoveries kept accumulating. In the year 2018, data from Hubble revealed water vapor in the atmosphere of another giant, WASP-39b. The pattern of its spectrum showed that water was present in a way that could be measured and modeled, deepening our understanding of how such planets form and evolve. And in the following year, attention turned again to K2-18b, that smaller world in the habitable zone. Hubble's observations detected water in its atmosphere as well, making it the first known case of water on a planet of that size and temperature in a region where liquid water might be possible. Each of these steps was like adding a new page to that cosmic scrapbook, a growing album of alien skies. Taken together, they hinted at something quietly hopeful, that water, often called the elixir of life, may not be a rare luxury confined to our own solar system. Instead, it might be fairly common in the atmospheres of distant worlds, waiting patiently in the dark, woven into clouds and vapors on planets we have only just begun to know. By now, our quiet scrapbook of alien skies has grown thick with pages, and each new page adds another ingredient to a kind of cosmic recipe book. With every observation, astronomers jot down more entries in that book: sodium and potassium, water and carbon monoxide, methane, hydrogen, helium, and many others. For a while, this list was shaped mainly by what our older instruments could manage to hear. They were most sensitive to large, hot planets, the kind that blaze brightly in infrared light and tug strongly on their stars. So the early chapters were filled with swollen hot Jupiters and puffy Neptunes, worlds where the heat makes gases easier to see. Those first recipes were simple, dominated by the same elements and molecules appearing again and again, not because the universe is plain, but because our tools were still learning to listen. Then came a turning point, a change as gentle and profound as a new lens being placed over an old eye: the arrival of the James Webb Space Telescope. Launched into the dark in the year 2021 and becoming fully operational in the year 2022, this golden-eyed observatory was built to drink in faint infrared light, the glow of warm dust, distant galaxies, and of course, exoplanet atmospheres. Once James Webb settled into its quiet perch far from Earth, it began to look closely at worlds we already thought we knew. One of its early targets was WASP-39b, a puffy hot Saturn-like planet where Hubble had previously glimpsed water vapor. James Webb did more than simply confirm what Hubble saw. It opened the spectrum like a fan and revealed a whole trove of chemicals, dancing in the starlight filtered through that planet's skies. For the first time in history, astronomers saw a clear, unmistakable signature of carbon dioxide in the atmosphere of an exoplanet. In the spectrum, there was a gentle rise, a peak sitting exactly where the fingerprint of carbon dioxide should appear, that little bump on a graph. A feature that might look unremarkable to anyone else sent a wave of quiet joy through the scientific community. Carbon dioxide is not just another gas. It plays a central role in shaping climates, storing heat, and recording a planet's geological and possibly biological history. On Earth, it flows from volcanoes, seeps from oceans, circulates through rocks, and is breathed in and out by life. James Webb did not stop at carbon dioxide. As more data from WASP-39b was carefully teased apart, the planet's atmosphere revealed sodium and potassium, water vapor, carbon monoxide, and something unexpected, sulfur dioxide. Finding sulfur dioxide on a distant planet was a genuine surprise. It hinted at the presence of photochemistry reactions driven by starlight, much like the way sunlight on Earth transforms oxygen into ozone high in our sky. This was not just a static list of ingredients. It was evidence of an atmosphere in motion, chemistry, unfolding under the constant touch of the star's light. It meant we were not only reading which molecules were present at that moment, but also catching them mid-conversation, watching an alien sky actively respond to its environment. One of the scientists guiding this work, Professor Natalie Batalla, spoke about how important this is. The discovery of photochemistry in the atmosphere of a hot Jupiter opens fresh paths to explore. Now, we are not only asking, what is there, but also, what is happening there right now? From James Webb's observations, the chemical composition of WASP-39b's atmosphere could be reconstructed with unprecedented detail. Ratios of elements, especially how much oxygen there is compared with carbon, told a deeper story. A high oxygen to carbon ratio suggests that this planet likely formed far from its star, in colder regions of the protoplanetary disk, where icy grains rich in water and other volatiles could accumulate. Later, it may have migrated inward, spiraling closer to its star until it settled into the tight, hot orbit we see today. In this way, the atmosphere is not only a present-tense description, it is a faint memory of the planet's childhood. Yet the reach of James Webb goes further still. Its mirrors and instruments are sensitive enough to begin sniffing the air of smaller, Earth-sized worlds. That promise drew many eyes to a nearby, intriguing system, TRAPPIST-1. Just about 39 light-years away, this ultra-cool star is dim and small compared with our Sun, but it is orbited by 7 rocky planets, each roughly Earth-sized. Their orbits are packed closely together, like beads on a string. Several of them lie within the star's habitable zone, where temperatures might allow liquid water to exist, at least in theory. For scientists and dreamers alike, TRAPPIST-1 is a quiet beacon of possibility. In the year 2023, James Webb turned its attention to the innermost of these worlds, TRAPPIST-1b. This planet orbits so close to its star that a year there lasts only a few days. It is certainly too hot to be comfortable, and no one expected it to be a second Earth. Still, the question was worth asking. Does it have an atmosphere at all? To find out, astronomers measured the planet's heat directly, watching the slight changes in infrared light as TRAPPIST-1b moved around its star. If the planet had a thick atmosphere, that blanket of gas would redistribute heat from the day side to the night side. The side facing the star would be cooler than bare rock, and the night side would be warmer, smoothing out temperature differences. The atmosphere would also leave fingerprints of absorption in the infrared spectrum. But the observations told a different story. The day side of TRAPPIST-1b glowed intensely, with temperatures consistent with a surface exposed directly to stellar radiation, with no insulating air to soften the extremes. The data showed no sign of the kind of heat redistribution a dense atmosphere would provide, and no convincing spectral features of a thick, gaseous envelope. Everything pointed toward the same conclusion. TRAPPIST-1b is most likely a bare, scorched rock, stripped by the fierce radiation from its star. For those hoping to find a cozy, Earth-like twin, this might sound disappointing. Yet, in another sense, it was a triumph of sensitivity and technique. James Webb had managed to weigh not just the mass and radius of a small rocky exoplanet, but the presence or absence of its air. If the star's harsh light has indeed peeled away TRAPPIST-1b's atmosphere, it offers a warning and a clue about how close-in planets fare around such stars. But the story of the TRAPPIST-1 system does not end there. Several of its siblings, especially TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, orbit farther out in cooler, more promising zones. They receive less brutal radiation and sit where liquid water might, just possibly, linger. These worlds are next in line for study, and many people who follow exoplanet science speak of them with a quiet, held breath. Do they have atmospheres? Are they thick or thin, cloudy or clear? For now, we wait, perched at the edge of answers. As our techniques grow more refined, our catalog of alien atmospheres continues to expand. It now includes not only hot Jupiters and warm Neptunes, but also so-called mini-Neptunes and a few tantalizing super-Earths. Each class of planet brings its own style of sky. Some worlds hug their stars so tightly that the temperatures are extreme beyond easy imagination. On these, metals in the atmosphere can evaporate on the sunlit side, rise into the air, and then condense into droplets on the cooler night side, falling as something like iron rain. It is a kind of weather that sounds like fantasy, but is carved into data as real as any rainfall on Earth. Other planets are wrapped in global decks of clouds made of sand-like or sulfur-rich particles. On such worlds, the skies might be thick and stormy from top to bottom, grains of mineral dust drifting and swirling where we might expect water droplets or ice crystals. Some exoplanets appear almost entirely veiled in haze, their spectra smoothed out by countless tiny particles that scatter light, masking deeper layers from view. In other cases, we see clearer, more transparent atmospheres where individual gases can be picked out cleanly, each absorption line standing like a letter in a well-written word. We have measured winds roaring through these distant skies, inferred from shifts in spectral lines that show gases rushing from hot regions to cooler ones at thousands of miles per hour. We have watched signatures of haze and cloud decks sharpen and fade as planets move through their orbits, suggesting storms and changing conditions. In some extreme cases, we have even glimpsed the escape of atmospheres themselves, the fingerprints of hydrogen and helium stretching outward, forming extended envelopes, and the faint traces of heavier atoms, such as titanium and sodium, drifting away into the void. All these textures of weather and chemistry have emerged from the smallest variations in light, turning faraway points into worlds that feel, in their own strange way, alive with motion. As our list of strange and beautiful atmospheres grows longer, A gentle question follows close behind it. When we manage to decode the air of a distant world, what are we truly hoping to see? We are not just chasing names of gases for the sake of a catalogue. Each molecule is a clue, a small lantern that can light up part of a planet's story. Some point toward geology, some toward climate, and a few, just a few, might one day hint at something living. Take carbon dioxide, for example, the simple molecule made of one carbon atom and two oxygen atoms, often written as CO2. On a rocky planet, carbon dioxide can seep into the sky from volcanoes, carried outward from deep inside, where heat and pressure stir old rocks into new forms. On a living world, it can also be part of the breath of a biosphere, exhaled by animals, released as plants and microbes respire and decay. On Earth, carbon dioxide is always with us. Volcanoes add it, oceans exchange it, and life constantly pushes it in both directions. So, when we find carbon dioxide in an exoplanet's atmosphere, we know that something active is happening. The planet is not a frozen, unchanging rock. There are processes at work, moving carbon from one place to another. But by itself, carbon dioxide is not a signature that says life. Our neighbor Venus has a thick, suffocating blanket of carbon dioxide in its atmosphere, enough to trap heat and drive temperatures to extreme levels. As far as we can tell, nothing alive stirs under those heavy clouds. The lesson is soft but clear. Context matters. A gas is only part of the story. The rest is told by temperature, pressure, other molecules, and the long history of the world beneath. Water vapor, the familiar H2O, has its own gentle voice. When we detect water in a planet's air, it may mean clouds drifting through its skies or even rain falling toward the surface. It hints that somewhere, conditions might allow liquid water to exist, at least in some layers of the atmosphere. That is why water vapor was one of the first molecules astronomers hunted for in exoplanet atmospheres, and why it remains one of the most cherished. On giant planets, the amount of water gives us a sense of how much oxygen they hold, and how they formed in the cold, icy outskirts of their systems before migrating inward. On smaller, rocky planets, water vapor becomes a key piece of the habitability puzzle. Its presence suggests the possibility of oceans or lakes, or at least an active water cycle with evaporation, condensation, and rainfall. Yet here, too, caution wraps around our excitement. Even Jupiter, deep beneath its visible clouds, is believed to harbor significant amounts of water. That does not make Jupiter habitable in the way we normally mean when we wonder about life. Water is one of the ingredients life loves, but it does not guarantee that a world is gentle, stable, or welcoming enough to host it. Then there is methane, a simple molecule of one carbon atom and 4 hydrogen atoms, often written as CH4. On Earth, most of our methane comes from living things, from microbes in soil and swamps, from the stomachs of cows and other animals, from slow, hidden processes in mud and ice. Some methane also trickles out from geological processes deep underground. In an atmosphere rich in oxygen, methane does not last very long. It reacts quickly and is broken down by sunlight and chemistry. That means that if we ever see a planet with both abundant oxygen and methane in its air, something active must be replenishing that methane against the odds. For many scientists, this combination oxygen and methane, sometimes written as O2 and CH4, feels like a dream signature, a possible whisper of biology. It would not be a loud, unquestionable shout. but it would be enough to make the world in question glow a little brighter in our imaginations. So far, we have not seen this particular pairing on any exoplanet. The telescopes are still learning to reach that level of delicacy, but we have detected methane on several giant exoplanets, especially the cooler gas giants, where methane remains stable and abundant. On these worlds, methane helps us understand temperature and chemistry rather than life. For example, the young planet HR 8799b, one of the 4 giants in that famous family portrait, shows methane in its spectrum. This places it in a category similar to a young T-type brown dwarf, an object that is not quite a star but hotter and more massive than a typical planet. In this case, methane tells us more about the planet's age, heat, and atmospheric layers than about anything alive. Still, every detection adds another line to our dictionary of what different gases can mean under different conditions. Our list of important atmospheric characters also includes oxygen and its close relative ozone. Free oxygen, the kind that pairs up as 2 oxygen atoms in a molecule, often written as O2, is restless. It prefers to bind with other elements, forming oxides and minerals. It is surprisingly hard to build up a thick blanket of oxygen in the air unless something keeps making it over long periods. On Earth, that something is photosynthesis. Plants, algae, and certain bacteria use sunlight to split water and release oxygen as a byproduct. The oxygen in every breath you take is, in a sense, plant light made visible. Because of this, many people imagine that finding oxygen in an exoplanet atmosphere would be a clear sign of life. The reality is softer and more complicated. So far, we have not yet detected oxygen on any exoplanet. Not clearly enough to be sure. The signal is faint, the distances are great, and even the James Webb Space Telescope struggles to pick it out. Future missions are being planned with this goal in mind, especially missions that will focus on planets similar in size and temperature to Earth, orbiting nearby stars. The hope is that, one day, we will see a clean oxygen signature in the spectrum of a rocky world. Still, even if we do, astronomers are careful not to let that single molecule speak too loudly on its own. In the late 20th century, when NASA's Galileo spacecraft was on its way to Jupiter, it performed a clever test. It turned its instruments back toward Earth and observed our home planet as if it were just another exoplanet in the dark. In the scattered light, Galileo easily detected oxygen and even methane, both present in substantial amounts. The combination strongly suggested a living world, and of course, we know that is true. Later, though, researchers asked a more unsettling question. Could there be ways to build up oxygen in a planet's atmosphere without life at all? Their studies showed that in some scenarios, a planet could lose its water to space. Intense starlight might split water vapor into hydrogen and oxygen high in the atmosphere. The lighter hydrogen could escape to space, leaving oxygen behind. Over long stretches of time, this process could create an oxygen-rich atmosphere without any biology. It would be a harsh, desiccated world, a kind of false positive for life. One Earth-based study concluded that while an oxygen-rich atmosphere is strongly suggestive, it is not a simple, undeniable proof of living processes. To feel truly confident, we would want to see oxygen alongside other signs, methane, or other gases that should not survive long in such an environment. Perhaps seasonal changes in gas levels that resemble the breathing of ecosystems, or even spectral hints of pigments like the breakdown products of chlorophyll, the green molecule that plants use to catch sunlight. Life tends to leave layered, overlapping fingerprints, not just a single mark, sulfur-bearing gases add yet another layer of nuance. Sulfur dioxide, made of one sulfur atom and two oxygen atoms, and often spoken of as SO2, and hydrogen sulfide, the simple H2S, can both serve as traces of geology and chemistry. On a volcanic world, sulfur dioxide might pour into the atmosphere from eruptions, mingling with water vapor to create volcanic steam and acid clouds. In the case of WASP-39b, the unexpected detection of sulfur dioxide was a sign of active photochemistry, the star's light driving reactions in the upper atmosphere, creating new molecules out of old ingredients. In a way, that sulfur dioxide is an alien cousin of smog, the kind of haze that forms in Earth's cities when sunlight interacts with pollution. On WASP-39b, there are no cars or factories, as far as we know, but the principles are similar. Starlight meets gas, and together they write new chemical stories. The atmosphere is not a quiet, inert blanket. It is a living reactor in the chemical sense, constantly rearranging atoms and molecules into new configurations. From all of this, a gentle conclusion emerges. There is no single molecule that can stand up and clearly announce, life is here. Not water, not carbon dioxide, not methane, not oxygen, not even a complex organic gas. Each one can be made in more than one way. Each can appear in more than one kind of story. What matters is the pattern they form together and the environment in which that pattern appears. Scientists speak of biosignatures, not as lone gases but as combinations of substances and behaviors that are difficult to explain without something alive in the mix. Often, this means looking for pairs or trios of gases that should not comfortably coexist. Oxygen and methane again, O2 and CH4, are one such pair. In an oxygen-rich atmosphere, methane is quickly destroyed. So if both are present in significant amounts over long periods, something must be adding methane back in. Another potential biosignature gas is nitrous oxide, sometimes called laughing gas, and written as N2O. On Earth, many microorganisms produce nitrous oxide as part of their metabolism. Finding nitrous oxide beside oxygen in an exoplanet atmosphere would be another intriguing hint that biology might be at work. On the other hand, there are what some call geosignatures, combinations of gases that tell us more about the geology and internal heat of a planet than about life. Sulfur dioxide, together with water vapor, can point toward active volcanism, plumes of steam and gas rising from vents or calderas. Large amounts of carbon monoxide, the CO molecule, along with hydrogen gas, H2, might suggest a world that has undergone intense heating, perhaps through strong stellar flares or a reshaping of its surface, leaving behind a chemically reduced atmosphere rich in these simple gases. As we gather more and more atmospheric profiles, each one a delicate fingerprint of a distant world, we begin to see patterns repeating. Some combinations of gases, temperatures, and pressures seem to shout, geology only, telling us that a planet is active but lifeless, driven by rock and heat alone. Others do not shout at all. They murmur. They lean toward imbalance, toward unstable mixtures that might require constant renewal. These are the atmospheres that make scientists sit up a little straighter, that whisper in the softest voice, maybe, just maybe. While we are learning to read these delicate whispers in the air of distant worlds, new instruments are quietly being prepared, waiting their turn to look up and listen. James Webb Space Telescope continues to astonish us with what it can pull from faint starlight. But astronomers are already shaping the next generation of planet hunters Machines that will widen and deepen our survey of alien skies. At the front of this new wave is a mission called Ariel, a spacecraft being developed by the European Space Agency and planned for launch in the late 2020s. Around the year 2029, Ariel has a single focused dream: to study the atmospheres of roughly 1,000 exoplanets. It will not try to do everything. Instead, it will specialize. Ariel will turn its attention mainly to warm and hot worlds, from scorched rocky planets to sub-Neptunes and full gas giants, and it will ask a simple but profound question of each one. What is your sky made of? Using carefully designed spectrometers, Ariel will watch stars as their planets pass in front of them again and again. Each transit will be an opportunity to capture starlight filtered through a thin shell of air. By splitting that light into its subtle rainbow and examining it in detail, the spacecraft will gather chemical fingerprints from world after world. Over time, this patient work will grow into the first truly large-scale catalog of exoplanet atmospheres, a kind of cosmic library of sky recipes. Scientists like Professor Giovanna Tinetti, who leads the Ariel project, sometimes describe this mission as a population census, but not of people or even of planets in the usual sense. It is a census of atmospheres, a survey designed to reveal patterns in chemistry across many types of worlds. Ariel will help answer questions that hang quietly behind every spectrum we take. How do planets with different mixtures of gases form and change over time? Why do some worlds carry abundant water and carbon dioxide, while others are almost completely dry or dominated by a single gas? How does a planet's distance from its star, its mass, and its history shape the air it ends up breathing? While Ariel gets ready to count and compare atmospheres, another great eye is being prepared across the ocean. Around the same period, NASA plans to launch the Nancy Grace Roman Space Telescope. Roman's main task will be to capture wide-field images of the universe, mapping dark matter, dark energy, and countless galaxies in sweeping views. Yet tucked within its design is something much more intimate for exoplanet hunters: a highly advanced coronagraph. This coronagraph will be one of the most complex instruments of its kind ever sent into space. Its purpose is both simple and magical. By carefully blocking out the light from a star, using masks and mirrors that must be aligned with exquisite precision, it will try to reveal the faint glow of planets that are tens of millions of times dimmer than their suns. It is a bit like blotting out the face of a bright lamp to see the dust motes drifting around it. If Roman's coronagraph performs as hoped, it will not only spot these dim companions, but also spread their light into spectra, allowing us to search for gases in their atmospheres. For the first time, we may be able to see exoplanets in visible light with this level of clarity, perhaps even noticing signs of changing seasons or shifting cloud patterns on some of them. A pale blue dot that grows slightly brighter or dimmer over time, or a world whose color changes subtly as storms wax and wane, could become more than a theory. They could become images we can point to and quietly marvel at. These efforts are stepping stones towards something even more ambitious: future missions that may one day photograph another Earth with enough detail to read its sky and, perhaps, glimpse the play of light on its oceans or the haze above its continents. Each new instrument is less a standalone leap and more a carefully passed baton in a relay that stretches across decades. Back on the ground, work continues in deserts and on mountaintops to build enormous telescopes that will complement these spaceborne eyes. One of the most striking is the extremely large telescope in Chile, with a primary mirror more than 128 feet across, made of many smaller segments that fit together like a mosaic. This vast mirror will collect starlight with incredible sensitivity, and with the help of sophisticated adaptive optics, it will sharpen that light, as if peeling away the blurring effects of Earth's own atmosphere. By coupling this colossal mirror with high-resolution spectrographs, ground-based observatories like the Extremely Large Telescope will be able to pick out faint atmospheric molecules in the light from nearby stars and their planets. In favorable cases, they may detect potential biosignatures on Earth-sized worlds, orbiting relatively close to us in cosmic terms. A tiny shift in a line here, a slight deepening of an absorption band there, and suddenly, the presence of oxygen, water vapor, or other gases becomes clear against the hum of the background. Looking even further ahead, into the years beyond the early 2040s, plans are being sketched for missions like NASA's Habitable Worlds Observatory, viewed as a successor to James Webb. While the exact details are still being refined, the overarching dream is crisp and bold: to directly image Earth-like exoplanets around nearby stars, and to search their skies for the faint, layered signs of life. Such a mission would use advanced coronagraphs, or perhaps even separate star-shading spacecraft, to block the light of target stars and reveal their planets with enough contrast to study in detail. If Habitable Worlds Observatory flies as envisioned, it will be able to look at a small but precious set of nearby systems where rocky planets occupy the gentle warmth of habitable zones. It will try to read the spectra of those planets' atmospheres, hunting for combinations of gases that, together, are difficult to explain without something alive beneath. It is a delicate, hopeful endeavor, to look for life not through radio messages or towering structures, but through the quiet breath of a planet written in starlight. When you step back from all these machines and missions, there is a sense of continuity that feels almost human in its tenderness. Each new telescope builds on the legacy of the ones that came before it. Hubble Space Telescope gave us our first hints, spotting the faint signature of sodium in the atmosphere of a hot Jupiter, and revealing that alien skies could be probed at all. Spitzer Space Telescope and the most precise ground-based instruments added more clues, inferring temperatures, winds, and the presence of water on scorched giants. James Webb Space Telescope is now unveiling a rich diversity of atmospheres, from hot Saturns laced with photochemistry to compact systems of rocky worlds that may or may not hold on to their air. Ariel will take those scattered discoveries and place them into a broader pattern, surveying hundreds upon hundreds of planets in a systematic way. Roman will push our abilities in direct imaging, showing us how to separate faint planetary light from the overwhelming shine of their stars. Ground giants, like the Extremely Large Telescope, will add razor-sharp detail from below, while future observatories in space will reach for ever fainter, ever subtler worlds. With each new eye turned toward the sky, the hidden faces of distant planets grow a little less abstract. What were once mere points of light become places with weather, chemistry, and history. Even so, there is still much more that we do not know than what we do. That imbalance is not discouraging. It is part of the wonder. It means there is room to be surprised. On a clear night, when you look up and see a scattering of stars, it is humbling to remember that around many of them, planets are turning, following their own slow orbits in the dark. Perhaps, among those countless systems, there is a world whose sky would feel strangely familiar if we could stand beneath it. A sky with soft clouds, a breathable mix of gases, and the same gentle blue that filters sunlight on our own world. We have not found that twin yet, but step by patient step, we are drawing closer. With each new telescope that opens its lens, with each carefully measured transit, with each spectrum captured and puzzled over long into the night, we sharpen our ability to recognize both the markers we know and those we have not yet imagined. The first time we see the atmosphere of a truly Earth-like exoplanet, it may not match our expectations. It might show a smear of industrial pollution, hinting at a civilization altering its air, or an unexpected balance of gases that forces us to reconsider what life can be and how it behaves. Our definitions may have to stretch and soften to make space for new stories. Or perhaps one quiet day, a telescope will reveal something that feels almost like a mirror, an atmosphere with nitrogen as its gentle backdrop, oxygen in healthy abundance, water vapor tracing clouds and rain, and a touch of reactive methane maintained in a delicate mismatch that hints at ongoing renewal. A combination so familiar that it makes the hair rise on the back of the necks of those who see the data for the first time. In that moment, the air of an exoplanet might seem to whisper through its spectrum, "This place feels like home." How we choose to respond to that whisper, whether with awe, caution, longing, or all of these at once, is a question we carry with us even now. The response itself is something we are still learning to shape. For the moment, the only answer waits out there, traveling across the darkness, in starlight that has filtered through alien skies and arrived gently at our mirrors and detectors. It is an answer woven into spectra and patterns, an answer we are finally starting to understand.